Good morning, everyone. There is no better way to start a Sunday morning than by doing some thermophysics problems, right? Just kidding. But that's exactly what I'm going to do now. I'm going to solve problem 5.8 from this textbook. It's a textbook that we're using for my thermodynamics class. It's the first thermodynamics class you encounter in your undergrad physics. It's called classical physics, but in my particular class, we're dealing with this more as an introductory statistical mechanics. And that textbook is the one that we are using. And so today I was going to talk about this problem. It was in fact one of my homeworks problems that I had to do this week. I just finished it on Friday, submitted, and am now preparing for the midterm that's coming up on Wednesday. And I decided to do this video or a few videos on some of the problems I'm going through as a preparation for the midterm. And I'm starting with this one because it's kind of an interesting one. And chapter 5 deals with chemical potential and Gibbs distribution. And as you can see, many of the problems are actually some real life problems, which is kind of cool. And that's one of the reasons I like this class, is because it's kind of hands-on, like you really get to see why some of that stuff that we're learning is important. And that's kind of matters to me when I'm studying. This problem is all about showing why carbon monoxide is such a poison to our bodies when it gets into our airways or the bloodstream or in the bloodstream. It's basically because the binding energies of the carbon monoxide molecules is significantly higher than the binding energy of the oxygen when one of these tries to bind to the hemoglobin in our bloodstream. And well, when the monoxide gets into the bloodstream, because it has higher binding energy, it is much more likely to occupy vacant hemoglobin sites, or even kind of push out the oxygen and take its place. And that's what we're going to calculate. The binding energy that is characteristic for the carbon monoxide and hemoglobin adsorption versus the binding energy of the oxygen to hemoglobin. At first, I'm going to show you some useful relations that we will be using for solving this problem. So the first will be the Gibbs factor. Then we would need the Gibbs sum. And also absolute activity is very useful, as well as fractional occupancy. I'm not going to go into details explaining each of these relations and where they came from, because I simply don't feel like I'm in a position yet to talk about this. But I think I know enough about that to be able to solve the problem. In short, in just layman terms, the Gibbs factor gives the probability of finding a system in a particular state with the particular count of particles, chemical potential, and the particular energy. Then the Gibbs sum basically sums over the denominator part of the Gibbs factor, but it sums over all possible states, so not just one particular. And then there is absolute activity, which, as far as I understand, and again in layman's terms, that usually when we try treating a certain thermodynamic system, we start with the assumption that it's our ideal gas or ideal liquid, and then we adjust for the differences from the ideal situation. And the absolute activity seems to be that adjustment from the deviation from the ideal situation. And then the fractional occupancy, which kind of seems very much the same as the Gibbs factor, but I still think that there is some subtle differences between the two, because that one will be used in the problem to calculate the number of hemoglobin sites occupied by oxygen. And I think that one is a little bit more general. I'm not sure, to be honest. So this is what we will be using mainly for solving the problem. Let's go straight into it. Okay, so the problem gives us the following information. We have the activity factor, the absolute activity of the oxygen, given to us as 1 times 10 to the minus 5. By the way, the absolute activity is usually a unitless quantity. Then we have the absolute activity of the carbon monoxide, which is 1 times 10 to the minus 7. We have temperature, which is the body temperature, 37 degrees Celsius, which in our problem we usually need to convert it to Kelvin. And also we would need to use absolute temperature later, so which by the relation like this can be easily converted. So where the K sub B is the Boltzmann constant. Okay, so that's what we will use for the temperature in this problem. Okay, now how do we approach this problem? We're given that this particular system in question can be in 3 states. We can have hemoglobin in the blood unoccupied, we can have it occupied with the oxygen, or we can have it occupied with the carbon monoxide if it enters the bloodstream. And so there are 3 possible states. And knowing this information, once we clarified on that, we can use our Gibbs sum to write this out for every single state that we are considering in the problem. And so then the Gibbs sum becomes okay, what I'm going to do, this is the exponent, and we can use the exponent rule to split this apart. This over this times this to the power of this. And then use this for each of the states. So for the first state, where we have no hem sites occupied by either oxygen or carbon monoxide, we will have the following. For the second term in this sum, we will be considering the situation where the hemoglobin sites will be occupied with the oxygen. Here, epsilon sub A is the binding energy of the oxygen to the hemoglobin. Okay, and the third situation will be describing the case when carbon monoxide will be binding with hemoglobin. Okay, so to summarize one more time, so this is vacant occupancy. So this is occupancy with oxygen at the binding energy epsilon sub A. And this is occupancy of carbon monoxide at binding energy epsilon sub B. You can simplify this. So this is 0, this is 0, so e to the power of 0 times e to the power of 0 is simply 1. This term can be simplified as follows, and here we can use our absolute activity definition, which is defined as epsilon to the power of mu over tau. Okay, and that is our expression for the Gibbs sum. Good. Now that we have that, we can go ahead and consider the first case where there is no carbon monoxide present in the system. And so we just consider the occupancy with the oxygen. For that, we will be using fractional occupancy. And this relation will give us the fraction of hemoglobin sites occupied by the oxygen. And from that, we can find what the actual binding energy for the oxygen is, because that's what our goal is. Oh, actually, I probably should have specified this in problem description. Okay, so that's what we need to find. And then compare the two to see why carbon monoxide is such a poison. By the way, this relation here, I found on the page 141 in the textbook. It's equation number 69. Okay, so for the first case, we need to find the number of hemoglobin sites occupied by the oxygen. Well, we need to find the binding energy for this situation where we know upfront that 90% of the heme sites are occupied by the oxygen, where there is no CO present in the system. So again, using our relation, we can write this like this. Okay, so in this situation, we have to be a little bit careful with what we write for our Gibbs sum. So this part on top here is the portion of the Gibbs sum that relates to the oxygen, which is this, and we want to find epsilon sub A. But the Gibbs sum at the bottom is where the caveat lies. When we look at the Gibbs sum, it considers all possible states, like no occupancy, occupied with oxygen, and occupied with carbon monoxide. But for the first step, we only consider the system where there is just two situations. There is no, like the hem sites either not occupied at all, or they are occupied to 90% with the oxygen. There is no CO2 present in the system. And so this term for the carbon monoxide won't come up in the Gibbs sum for the first case we're considering. We also know that our fractional number of the heme sites occupied by oxygen is 90%, which is, well, 0.9. Here we know basically every single quantity except our binding energy, and that's what we are trying to find. Okay, simplifying this and some rearranging gives us the following. Okay, so some rearranging and substituting 0.9 for F led us to this expression, which is when we take natural log on both sides, we end up with the following. And then some further rearranging, solving for epsilon sub A. Okay, so this is our final expression to find our binding energy for the oxygen. Substituting all the numbers, all the quantities we know from the problem, we can easily now solve for epsilon sub A. But keeping in mind that the actual question asks us to find that energy in electron volts. So whatever answer we get here, we would need to convert to electron volts because the answer will be given in joule. So this is what I've got so far. I substituted Boltzmann constant in, and then our temperature, and taking the natural log of this fraction gave me this result. This is the joule, actually, the units of joule in SI units. And now we need to convert this to electron volts. So we do that by multiplying by the following. 1 electron volt. And 1 electron volt is equivalent to 1.602 approximately times 10 to the minus 19 well, it's joule, so it's the same units as here, and then after that they will cancel, like these things will cancel, and after putting that in the calculator, we get our binding energy of the oxygen as 0.366 electron volt. And this is our answer for part A of the problem. Well, now that we have found epsilon sub A, we go over to solve the part B of the problem, where we need to find epsilon sub B, binding energy of the carbon monoxide. And in this case, we consider the system in all three states at the same time, which is vacant Hem sites, Hem sites occupied with oxygen, and Hem sites occupied with carbon monoxide. We use exactly the same procedure as we used in part A, so we can use the fractional occupancy relation as well. And here in this part, it's kind of easy to make a mistake, because when I was doing it the first time around, I did it wrong. I assumed that we would have to use the state describing actually the carbon monoxide in that fractional occupancy relation. And so I put this term on top of that and used the Gibbs sum in its full form, which is correct, but then using the state description of the carbon monoxide on top was wrong. It's because we're still considering the fractional occupancy of the oxygen, just including the carbon monoxide in the Gibbs sum to calculate our binding energy of the carbon monoxide. So it's still lambda sub A on the top with its corresponding binding energy that we just found in the first part. And then we're using the Gibbs sum in its full form for all three states. Okay, and now from this expression here, we need to solve for epsilon sub B. In this case, the fractional occupancy of the hemoglobin with oxygen is given as only 10%, and the rest is occupied with carbon monoxide. So F in this case is just 0.1 instead of 0.9 as we had before. And so using this number, we rearrange this expression and solve for epsilon sub B. Oh, and actually something to simplify our calculations. If we look at this term here up top, substituting each of the quantities we know, and we know them all, works too. It's just very time consuming and prone to mistakes, and that's what I did too until I realized that we can use this here, this expression, because if you look at this, the product of lambda sub A and exponent is equal to 9, and that's what we're going to use on top of here. It's just equal to 9, the same as here. And so this then becomes 9, 1 plus 9 plus lambda sub B. And so simplifying. Okay, so doing all our simplification and using this expression and this as equals to 9 because of this, we arrived at this expression eventually, and then substituting all the numbers, converting to the electron volts, we get this value for the binding energy of the carbon monoxide. And if you compare these two, clearly the carbon monoxide binding energy is significantly more than the binding energy of the oxygen. So when it gets into the bloodstream, it has much better chance to bind to hemoglobin sites and even replace the oxygen relatively easily, and that's why it's such a poison.